The central limit theorem is one of the most powerful and amazing ideas in statistics. The normal distribution is this handy curve that is unimodal, symmetrical, and just generally awesome, in my own words here. It forms this perfect mathematical curve. The problem is that in the real world, most distributions kind of look like this. They're somewhat unimodal, maybe sometimes, maybe not always. Kind of symmetrical, maybe not always. But basically you can see this is awesome, this is not. The good news is the central limit theorem has the power to turn all kinds of distributions into normal distributions. So let's take a look. Here on top we have a normal population. So let's imagine that you're measuring something like height in the population. It's going to follow a normal distribution, each individual one at a time. And down here we're sampling. So let's say we take a sample of one person at a time. It's going to follow the exact same curve. That makes sense. But as you increase your sample size to 2 and then take the average of those two and plot that on a graph, you notice that the curve got a little bit tighter together. And as you get up to 3, 4, 5, the curve continues to get closer and closer and closer to itself. It gets narrower. The standard deviation is going down. And you can see here, standard deviation of this curve down here, 0.485, up here 1.643. It's much smaller. If I go back to a sample size of 1, you can see that the standard deviation 1.6 something, 1.6 something are basically the same. But as you increase that sample size, that standard deviation gets smaller and smaller. That curve gets tighter and tighter together. And the overall graph gets much narrower and narrower. Now, that's kind of neat, and that's something that we probably saw when we looked at confidence intervals earlier, when our distribution would get closer and closer together because we were able to make better predictions with more data in each sample. Here's something that you probably wouldn't expect, though, about the central limit theorem. Let's take a crazy bimodal graph like this. A few very low values, 0, 1, 2, and a few very high values like 8, 9, and 10. And if that's our population, when we take samples of size 1, we're going to get exactly what we expect. Some very low values and some very high values. But if we up the sample size to size 2, now we get something interesting happening. If we get 2 low values, we get something down here. If we get 2 high values and take their average, we get something up here. But if you get a low value and a high value and take the average, it's going to be in the middle. And so half of the values that result end up being in the middle. And now when you take a sample size of 3, you get a similar effect, just more crazy. All 3 are small. You get 2 small and 1 big, 2 big, 1 small, 3 big. And if you go up to 4, you kind of see that repeated effect. All small, 1 big and 3 small, 2 and 2, and so forth. And as you keep upping that sample size, you get more and more of these peaks, until what starts to happen is these peaks bleed into each other. And as your sample size gets bigger and bigger and bigger and bigger, all of a sudden it forms into, you guessed it, a normal distribution. And the standard deviation continues to go down as the sample size goes up. Your precision on your guess gets better and better. But the key thing that's different than what we looked at before is not only is the curve getting narrower, but the shape is changing, and it's changing specifically into the normal curve. And you can see now we're up at sample sizes in the 80s, and by that time it almost forms a perfect normal curve. So you can see that normal curve really started to form when our sample size got around 40 with some of the most extreme distributions. If you were to take something that's a little less crazy, like let's say a flat distribution here, it's not going to take quite as big of a sample size to turn it into a normal curve. So let's go ahead and reduce our sample size here to 1, And of course, when it's a sample size of 1, you get exactly what you expect up here. But as we get to 2, it gets kind of triangular, 3, 4, 5, and by the time you're looking at maybe 12, 13, 14, 15 values in your sample, you're starting to see a normal curve. So depending on how extreme and crazy the original population is, it will affect how long it takes, how big of a sample it takes in order for the plot of all the sample averages to form a normal curve. Now, again, the first power of the central limit theorem is that with a large enough sample, it turns any distribution into a normal curve. And remember, it turns the distribution of sample averages of x bars into that normal curve. A chart that you might want to reference later, I'll go through it quickly, is when you have a small sample size, if you want to end up with a normal curve, you better start with a perfect normal curve. If you have a sample size maybe 5 to 10, your starting distribution better be roughly normal, unimodal and symmetrical. If you have a starting sample size of around 15, you can have a little bit of skew going on, maybe a uniform distribution, and then it should be able to turn normal. If you have sample sizes of 30 or even as high as 40, it kind of doesn't matter what you start with for your distribution, because with sample sizes this large, we saw that even that really extreme bimodal distribution could turn into a normal curve. So pretty much anything goes once you get up into the higher sample sizes. And I'll just look at this below here. You can see that not only does the curve become normal, but it also becomes narrower and narrower as your sample size gets bigger. So quick check to make sure that we understand the concept. Is the sampling distribution going to come out normal? If you start out with something like this, kind of bimodal, and you have a sample size of only 11, I'm going to say no, it probably does not become normal. That's probably too small of a sample to make that become normal. If you have something here that's roughly unimodal and symmetrical and you have a sample size of 16, yeah, that's going to be just fine. That's going to work out. And then here, some kind of a crazy distribution, maybe 2 or 3 peaks going on, but it's got a huge sample size, 37. We said anything in the 30s and 40s and above, pretty much anything goes, and you're going to end up with a nice, clean, normal curve. So this one's going to be all right. So these two would both work out. This first one is a little bit too crazy to have a sample size of only 11 to turn it into a normal curve. Second power of the central limit theorem talks about the mean and standard deviation. Now the mean doesn't change. The middle of all the graphs in our simulations, you can see that the middle was 5 up here, it's 5 down here. Even with the bimodal, the middle is 5 here, it's 5 down here. Not going to change. But the standard deviation gets smaller, and it gets smaller in a predictable way. What you can do to calculate how small it's going to be is you take your original standard deviation of your population, whatever that happens to be, and you divide it by the square root of the sample size. Now, n always represents the sample size. I'll just write that in here. So the square root of however big our sample is, we divide it by that from our original population standard deviation, and that will give us the standard deviation of our new graph, our graph of x bars. The reason we use the different notation down here, sigma with a little x bar versus sigma with a little x here, is that it lets us tell the two standard deviations apart. This one's our original one for the whole population with a little x. This one is referring to our new curve based on sample averages, thus the x bar. So going back to the example, what would the different standard deviations be of the sampling distributions that result? If we had a sample size of 11, regardless of what the shape is, our standard deviation of 3.7 is going to get divided by sample size of 11 square rooted. So 3.7 divided by square root of 11. So I've typed this into my calculator. So that means that the new standard deviation is going to be smaller, and in particular is going to be a standard deviation of 1.12 when our original starting one was 3.7. Next one here, we have a sample size of 16, original standard deviation of 19.71. Again, all we do is take our original standard deviation, 19.71, and divide it by the square root of 16, which hopefully you know is just the square root of 4. So 19.71 divided by, and I'll just type it in here, square root of 16, but again we could just divide by 4. And that's going to be 4.93 if we round that off. And then same idea with the last one. We take our original starting one, our 0.59, and we divide that by the square root of our sample size, which is 37. And so that's going to be divided by about 6, so we should be expecting something around 0.1 here. And if we do this in our calculator, we find that it comes out to 0.097. We'll round that off to 0.097. So a quick review. Turning distributions into sampling distribution by averaging the different samples together. So you take a sample, you find the average, throw it back. Take a new sample, find the average, throw it back, and plot what that looks like on a histogram. And here's what happens. The shape becomes more normal. So whatever you start with, you end up with something that looks roughly like a normal curve as long as your sample is big enough. Standard deviation gets smaller. So if you start out with something with a certain standard deviation, the curve is going to get narrower to show how precise your ability is to estimate or guess. And the mean does not change. The center of this graph is going to line up with the center of this graph, line up with the center of any original starting population. So any sample size and the starting population are all going to have the exact same average or center that you go with. Quick example to practice this. Let's say you take an SRS of 25 runners and it yielded a mean time of 19.65 minutes with a standard deviation of 1.36 minutes. Will our standard deviation follow the normal curve? Our hints here are going to be our sample size and then the situation itself. Runners usually follow a somewhat unimodal or symmetrical distribution. You have a few people that are very fast, a few people that are very slow, and a bigger pack in the middle. Is it going to be a perfect normal curve? No. So we might get something that looks kind of like this as our initial distribution. Not a perfect normal curve. However, something that's pretty close with 25 runners is going to form a very beautiful, perfect textbook curve. So as long as we start with something decent, 25 runners is enough to make it, yes, follow the normal curve. What is the standard deviation of the sampling distribution? Well, we start with our population standard deviation, that 1.36, and we divide it by the square root of our sample size. So if we do that here, we have 1.36 divided by square root of 25, which is 5. So 1.36 divided by 5 is going to be 0.272. And so that's the standard deviation of the sampling distribution, which we would write as sigma x bar. And then our best guess of the mean of the sampling distribution, remember that the mean doesn't change just because we're taking samples. The estimate of the mean should always be the same. So 19.65 minutes. Exactly what we had in the original problem. And that is the central limit theorem in a very large nutshell.